In the previous video, we were working with the data for which we had a nice description. That is, we knew what the features were, and the data was given us as is, without severe modifications. But it's not always the case. The data can be anonymized and obfuscated. In this video, we will first discuss what is anonymized data and why organizers decide to anonymize their data. And next, we will see what we as competitors can do about it. Sometimes we can decode the data, or if we cannot, we can try to guess what is the type of the feature. So let's get to the discussion. Sometimes the organizers do not want some information to be revealed, so they make an effort to export competition data in a way one couldn't get a value out of it. Yet all the features are preserved and the machine learning model would be able to do its job. For example, if a company wants someone to classify its documents, but doesn't want to reveal the document's content, it can replace all the word occurrences with hash values of those words, like in the example you see here. In fact, it will not change a thing for a model based on bags of words. I will refer to anonymized data as to any data which organizers intentionally changed. Although it is not completely correct, I will use this wording for any type of changes. In competitions with tabular data, companies can try to hide information each column stores. Take a look at this dataset. First, we don't have any meaningful names for the features. The names are replaced with some dummies. And we see some hash-like values in columns x1 and xx. Most likely, organizers decided to hash some sensitive data. There are several things we can do while exploring the data in this case. First, we can try to decode or de-anonymize the data, in a legal way, of course. That is, we can try to guess true meaning of the features. Sometimes de-anonymization is not possible, but what we almost sure can do is to guess the type of the features, separate them into numeric, categorical, and so on. Then we can try to find how features relate to each other. That can be a specific relation between a pair of features, or we can try to figure out if the features are grouped in some way. In this video, we will concentrate on the first problem. In the next video, we will discuss visualization tools that we can use both for exploring individual features and feature relations. Let's now get to an example how it was possible to decode the meaning of the feature in one local competition I took part. So, I want to tell you about the competition I took part. It was a local competition, and the organizers literally didn't give competitors any information about the dataset. So they just put the link to download the data on the competition page and nothing else. So let's read the data first. And basically what we see here is that the data is anonymized. So the column names are like X something, and the values are hashes. And then there are some numeric values in here, but, well, we don't know what they mean at all. And basically, we don't know what we have to predict. We only know that it is a multi-class classification task, and we have 4 labels. So, as long as we don't know what the data is, we can probably build a quick baseline. Let's import random forest classifier. Of course, we need to drop target label from our data frame as it is included in there. We'll fill null values with -999, and let's encode all the categorical features that we can find by looking at dtypes property of our data frame. So we will encode them with label encoder, and it is easier to do with function factorize from pandas. So let's fit random forest classifier on our data. And let's plot feature importances. And what we see here is that feature X8 looks like an interesting one. So we should probably investigate it a little bit deeper. So if we take the feature X8 and print its mean and std value, they turn out to be quite close to 0 and 1 respectively. And it looks like this feature was standard scaled by the organizers. And we don't see here exactly 0 and exactly 1 because probably train and test was concatenated when the data was scaled. So if we concatenate train and test, then the mean will be exactly 0 and the STD will be exactly 1. Okay. So let's also see are there any repeated values in this feature. So we can do it with a value counts function. Let's print first 15 rows of value counts output. And we can see that there are a lot of repeated values. So like they repeat 1,000 times. All right. So we now know that this feature was standard scaled. So probably we can try to scale it back. So the original feature was multiplied by a number and was shifted by a number. So all we need to do is to find the shifting parameter and the scaling parameter. But how do we do that? And is it really possible? So let's take unique values of the feature and sort them. And let's print the difference between two consecutive numbers in this sorted array. And look, it looks like the values are the same all the time. So the distance between two consecutive unique values in this feature was the same in the original data too. It was probably not 0.043 something. It was, who knows, it could be 9 or 11 or 11.7, but it was the same between all the pairs. So assume that it was 1 because, well, 1 looks like a natural choice. So let's divide our feature by this number, 0.043 something. And if we do it, yes, we see that the differences become rather close to 1, and they are not 1 only because of some numeric errors. So yes, if we divide our feature by this value, this is what we get. All right. So what else do we see here? We see that each number, it ends with the same values. Each positive number ends with this kind of value and each negative with this. Look. So it looks like this fractional part was a part of this shifting parameter. So let's just subtract it. And in fact, if we subtract it, the data looks like in integers actually, like it was integer data, but again, because of numeric errors, we see some weird numbers in here. So let's round the numbers, and that is what we get. This is actually on the first 10 rows, not the whole feature. Okay, so what's next? What we did so far? So we found the scaling parameter. Probably we were right because the numbers became integers, and it's a good sign. We could be not right because probably, who knows, the scaling parameter could be 10 or 2 or again 11, and still the numbers will be integers. But 1 looks like a good match. It couldn't be at random, I guess. So, but how can we find the shifting parameter? We found only fractional part. Can we find the other? And can we find the integer part, I mean? So it's actually a hard question because, well, you have a bunch of numbers in here and you can probably build a hypothesis like, well, it could be something, and the regular values for this something is like that, and we could probably scale it, shift it by this number, but it could be only approximation in our hypothesis. And so our journey could really end up in here. But I was really lucky, and I will show it to you. So if you take your X8, I mean our feature, and print value counts, what we will see this number 11, 17, 18, something. And then if we scroll down, we will see this minus 90, 68. And it definitely looks like a year of birth, right? So immediately I had a hypothesis that this could be a text box where a person should enter his year of birth. And well, most of the people really entered their year of birth, but one person entered 0. Or the system automatically entered 0 when something wrong happened. And well, that is the key. So if we assume the value was originally 0, then the shifting parameter is exactly 9068. So let's try it. So let's add 9068 to our data and see the values. Again, we will use value counts function and we will sort the values. So this is the minimum of the values. And in fact, you see the minimum is 0 and all the values are not negative. And it looks really plausible. So take a look, 999. It's probably what people love to enter when they are asked to enter something. Or this 8099. It could be a default value for this text box, so it occurred so many times. And then we see some weird values in here. People just put them at random. And then we see some kind of distribution over the dates that are plausible for people who live now, like 9080, well, maybe 9038. I'm not sure about this. And yes, of course, we see some dates from the future. But for sure, it looks like a year of birth, right? And yeah. Well, the question, how can we use this information for the competition? Well, again, for linear models, we probably could make a new feature like age group or something like that. But in this particular competition, it was no way to use this knowledge. But it was really fun to investigate. I hope you like the example. But usually it's really hard to recognize anything sensible like a year of birth in anonymized features. The least we can do is to recognize the type of the feature. Is it categorical, numeric, text, or something else? Last week we saw that each data type should be treated differently, and more treatment depends on the model we want to use. That is why, to make a stronger model, we should know what data we are working with. So even though we cannot understand what the features are about, we should at least detect the types of variables in the data. So take a look at this example. We don't have any meaningful column names, but still we can deduce what the feature types are. So x1 looks like text or categorical data, x2 and x3 are binary, x4 is numeric, x5 is either categorical or numeric, and more, if it's numeric, it could be something like event counters because the values are integers. When the number of columns in the dataset is small, like in our example, we can just print the table and manually sort the types out. But what if there are thousands of features in the dataset? There are useful functions to facilitate our exploration. Function dtypes from pandas guesses the types for each column in the data frame. Usually it groups all the columns into 3 categories: float, integer, and so-called object type. If dtype function assigned float type to a feature, this feature is most likely to be numeric. Integer typed features can be either binary, encoded with 0 or 1, event counters, or even categorical, encoded with the label encoder. Sometimes this function returns type named object, and it's the most problematic. It can be anything, even a regular numeric feature with missing values filled with some text. Try it on your data and also check out a very similar info function from pandas. To deal with object types, it is useful to print the data and literally look at it. It is useful to check unique values with value counts function and nulls location with isNull function from pandas. In this lesson, we were discussing 2 things we can do with anonymized features. We saw that sometimes it's possible to decode features, find out what this feature really means. And no matter we understand the meaning of the features or not, we should guess the feature types in order to pre-process features accordingly to the type they have and selected model class. In the next video, we will see a lot of colorful plots and talk about visualization and other tools for exploratory data analysis.